phase change or a tipping point right now, and it's just even more exciting if you view the challenges as exciting, and I certainly do. This is a great time to be in the business. So as Paul noted yesterday, and apologies for all the acronyms, but I'm going to be speaking later on after a kind of an early introduction about the applications that we're looking at in Exascale computing project, and these are a broad set of applications across the DOE science and energy portfolio. So I'm going to take you quickly through what we're seeing from leading researchers in the nation with regard to the types of problems they can solve. I'm not going to dive into the details of the applications or the algorithms unless you want to talk offline. I'll do what I can to answer questions. Some cases I can answer them well, other cases I'll point you to people. But you guys, this program is actually supported with an ECP within this blue box, which Paul has charged me to coordinate along with my colleague Bert Stilt at Lawrence Livermore. And I'll just say, here's my before photo. That was my third grade picture, and I was crying before the photo, and my mom tells me, I don't know why, I think it was kind of a wimp back then, maybe I still am, but in any case, here's my before picture. I've been involved in this activity about a year, and we're ready to get rocking and rolling, and I think we're about to be there. So a little bit about myself. I've built a lot of codes in my past and over 30 years. Although lately I'm your tax dollars at work, meaning I'm leading and managing, so I'm not doing the fun stuff. But it is the cult of the code in that I think applications developers and software developers in general really feel like it's like a painter, and really feel like your software is your painting, and you become emotionally attached to it. So I call it the cult of the code because I think too often we think of these great names and all this wonderful stuff we did instead of realizing what's really important is the knowledge embodied in the applications, not the applications themselves. I think what's happened in the past 10 years, and this is again very sort of parochial from my point of view, applications are where theory and experiment come together and live. I don't really even view it as a third tier. I really view it as the integrating factor. And these large computers are really numerical laboratories where we can view them as time machines and ask what-if questions for various phenomena that we want to be able to simulate. And we're getting better at being able to predict with quantitative accuracy. So when I got involved in this activity in the mid-'80s, I was looking at ICF target design, and I was working with a guy named Jerry Brackpool who just been working on a particle and cell method. It was a way cool method to push particles around on a mesh to simulate fluids and solids. And it was invented by Frank Harlow, by the way, at Los Alamos in the 50s. And Frank sadly passed away just a month ago. He's really the father of particle and cell. And I noticed that this method we developed was called FLIP, and Jerry Brackpool developed it, and I was one of his PhD students. And it was a kind of a modernization of PIC. And FLIP sort of sat dormant for 10 or 15 years. Not many people picked it up and used it, and its variant is called the material point method. So it's using particles not only for simulating fluids, but also for solids. Well, the computer graphics industry has picked this up in the past 15 years. And there's again, this is some old simulations that I did. Okay, back then, conjugate gradient, we were just getting our feet wet with Krylov methods, and I was using, God forbid, Fortran 77, CDC 7600, Cray XMP. This was kind of 85 to 87. So big calculations were 20 by 20 2D meshes. Okay, so very different time. But let me show you what Walt Disney, and in fact, Joey Turan, he goes by Joey. He's a math professor at UCLA. They picked up this FLIP method that we worked on in the late 80s. We only found this out about 6 months ago. And he and his colleagues at Disney Animation are now using it for animation, and they're solving real 3D Navier-Stokes and real 3D materials response. So what you're seeing in movies like Frozen are actually science simulations. Okay, so that's something you saw from the movie, okay? But let me point out that the snow is being simulated with the material point method. So you have fixed mesh. They're running about 100 million particles, surprisingly small simulations of kind of 10 to a few thousand processors. Initially they're using OpenMP, and they moved to thread building blocks. It's written in C++, and actually this code is going to go open source because Joseph really wants to win a Technical Academy Award. And you really do that by getting your technology out there. He just sent this to me today. But let me show you something even more interesting. This is, now we're simulating melting, okay? We're doing phase change and heat transfer, and he's using particles, and there you see the particles. So fixed mesh, particle in cell. The material point method was invented at Los Alamos and University of Mexico by Deborah Solsky in kind of the early 90s. And they're doing some fantastic things for this. So I go visit Joseph at UCLA about 6 months ago saying, hey, this is way cool stuff. We want to use it for science research and DOE, and particles really map really well to exascale. So one of the applications we're looking at is additive manufacturing or 3D printing, okay? And we think this is going to be a perfect technology to model the actual 3D printing process. And I'll take you through some reasons why we think that's needed. In any case, it's exciting, it's also kind of sad that, it takes another group to really pick up your stuff and make it way cool. So in terms of my own background, application development, spent a lot of time modeling surface tension, again, back in the early 90s. And here are the challenges. They're trying to model complex topology interfaces moving through the domain. I put the Sally Ride word down there because she came and visited Los Alamos once and showed a movie of her in the shuttle where she opened a pouch of orange juice, and it's just pulsating blob of orange juice in front of her, and she drank out of it as it's floating in front of her. At the time, I was working on modeling surface tension for NASA in zero gravity, so that really got me pumped up to do a better job, because fluid flow in zero gravity is very non-intuitive. Things like reorientation, these are simple 2D, 2D simulations of you want to reorient propellant in a tank, and if you're in zero gravity, you don't know where, if it's partially full, you have no idea where the bottom and the top is, so you have to fire thrusters to orient the fluid down to where you can pump it out. Those sorts of applications are really way cool things you can do in this space. In this case, it's just knowing how to build 2D or 3D Navier-Stokes solvers with interfaces. I'm really a believer in you can build it and application developers will come. That said, in talking to Paul, with the Exascale changes we see, we need to invest heavily in the applications. We really have a lot of challenges. I think David Keyes and others will probably talk to you about that with regard to the challenges in applications. Whole new algorithms need to be developed and sort of rethought. But back when I was at Los Alamos, my program manager brought the connection machine in, and we did not have one code that could run on that machine. I don't think you could purchase a system today and have that be the situation. But it was one of the funnest times for me, because for 2 or 3 years I got to write a code from scratch. At this time, when this machine came in, and now you have connection machines kind of on a board, right, on one GPU, but actually you can see 131 gigaflops peak. But there was something called a C-star compiler, and then later a CM Fortran, which was an early version of Fortran 90. So my assignment was to rewrite a shock physics code. It was called Pagosa, and here this is a simulation of oil well perforator run on the connection machine, and you can see we were using a whole 2 million cells and 3 gigabytes of memory. But we were porting a code. In the process of porting, we realized, well, we can make this algorithm better, and we can do that better, and we should have different data structures. So we ended up just rethinking the whole code, and it ended up being a much better code in terms of algorithms and accuracy and data structures that actually ported back onto some of our other systems and ran, guess what, a lot better. But this, you can also see here, I think the first supercomputing was maybe late 80s, maybe Bill can tell me. That was SC91 where we presented that. So again, some way cool stuff with applications, or at least from my perspective. And I've also taken these sorts of techniques and modeled gravity pour casting and welding. And so my training, my own personal training is nuclear engineering, which is really mechanical engineering, I think, in cylindrical coordinates. That said, I'm more of a computational engineer, which means that if you have fluid flow and heat transfer and phase change and material response at your disposal, you can model all kinds of interesting things, and that's kind of what keeps me up. An example here, we were trying to model just how does let's see if I can get this to go. how does a mold fill? Okay, this is supposed to be molten aluminum filling a mold, and the riser narrows down because of as the fluid accelerates, it will neck down. So you try to neck down with the fluid. And this is a blind simulation. Movies were taken of the fill, and we got the fill totally wrong. We had the splash, when it started to fill up the little box, we had the splash going left, and because our turbulence model was wrong, the splash should have gone right. So we totally missed the way the mold filled. You might not think that matters, but in a lot of these scenarios, you're aggressively cooling the mold as it's filling, and so if you don't, wherever the molten metal is where there's lots of heat transfer. So you don't get the metal right, you're going to get the freezing process wrong, and hence the microstructure wrong. But then we had a guy at Cornell that picked up the same code that we're using for free surface flows, modeling how molds filled, and he was modeling it for dam break bore interactions and basically ocean hydrodynamics. So here you have a 3D interfacial flow code that we built for filling molds and casting, and Philip here has really made a great career out of trying to understand how to build docks and decks and dikes on for ocean-going challenges. So a lot of exciting things when you're in application space can happen. Some planned, some not. And so this just gives you kind of a quick overview, maybe to motivate you to think about applications, because that's certainly an area where we need lots of good folks. I think Paul talked about the NSCI, which is another really exciting initiative, and the Exascale computing project is really, one of DOE's responses is to stand up this important project. And there you see the presidential orders on the left, and then I think Paul also showed, the various application spaces. And when you read the NSCI strategic plan, what is front and center is critical applications for the nation. Which is very exciting, because applications, I'm going to define critical applications as one that can inform decision and policy makers with high confidence solutions. An application never makes decisions for you, or at least it shouldn't, but it can inform decision makers with high confidence results. And that's what we're looking at here with ECP. The overall strategy, again, taken right from the project's mission need, is to support the science programs in the DOE, and I think I have an org chart that kind of shows you what that looks like. But there are 5 program offices that are engaged in fundamental and applied research directly in support of our energy portfolio, and you can see some bullets there. I'll get into some details in a few later slides. We have national security needs to support, and you see the bullets there. And then there's some example applications. Obviously, materials discovery and design is really very, very important. Materials are ubiquitous across everything we do and we know. And we've really moved from, casting, we called it pour and pray or heat and beat, but basically gone from making something and then cutting it open and seeing what's in there and then trying to understand what its properties are. Now with the computer, we can really design materials with properties that we want, and so we basically then we make the end product knowing how it's going to behave, or at least in many areas that's where we're moving. But you see other areas: nuclear energy, large data applications, of course, national security, client combustion, fusion, additive manufacturing, and that's what I called earlier 3D printing. But additive manufacturing, I think, will be really well tackled by that Disney MPM method that I showed earlier. So our own strategy within Paul's project that I'm leading the applications area, but in reporting to Paul, our goal is to really precipitate, foster, and grow a national push in applications, and that means we've got to deliver to 10 stakeholder program offices. SC here is an acronym for Office of Science. Okay, so there are 5 offices there, 4 applied energy offices, and the NNSA defense programs. But there's also some NSCI deployment agencies. We're looking first and foremost at the NIH. When I say we, the DOE project folks, the Department of Energy personnel across the 17 national labs and a lot of the universities that we fund have a lot of the world-leading experts in computer science and applied math and computational science. And so here's where we can sit down with these deployment agencies, and they're the domain scientists and the experts, and we can help them to put together large applications that can be consequential with regard to their mission needs. We want to support a number of national key initiatives. One way to sort of rack and stack the applications is say, what areas of our national, sort of strategies does this application point to? We got to make sure we want to cover all these areas. And there's six areas listed there that I'll get to here in a little bit. We also want to make sure that the applications we support really drive a broad set of requirements for the ecosystem in the exascale and beyond. In other words, if we have all particle and cell codes, even though that would be way cool, we would probably miss a lot of the application space that matters, and our software ecosystem could be too hardwired to say PIC codes and not support other capabilities. So it's important to make sure that our applications really drive a broad set of software requirements. And we're looking at an aggressive push with regard to supporting application teams that are, not just a few people, but maybe 10, 15, 20 people, because our experience in these large, complex multiphysics applications, and they may end up having 2 or 3 million lines of code, require groups of large teams. And we've learned a lot. In fact, we've learned a lot from industry. Your Googles and your Yahoos and other companies that are doing lots of agile software development with regard to how to be better and more productive in our own development process. So again, you can't see the org chart there, but I'll just point. The blue arrows are areas, program offices where ECP is targeting. Okay, so there are lots of program offices, and I think I have a chance to dive into those different offices as I take you through some example applications that we're looking at. Again, this is an eye chart, but I want to share with you. For an ECP, for the first round of applications we're looking at supporting, there's order 30 that are candidate applications. We're probably not going to be able to support them all, but when we worked with the 17 DOE national labs, we kind of worked our way down to this set. And each application represents a high priority for a particular program office, okay? So had to be programmatically mission impactful, but also we had to have good quality teams with good quality plans that could deliver an application. It could be created from prototype, it could be taken a mature code to kind of the next level within sort of a 5-year window. So in energy security, I'll just start there. We have wind plant design, we've got design commercialization of small modular reactors, we have materials for harsh environments, nuclear fusion and nuclear fission environments. We've got subsurface simulations, really very important for oil and gas, for geothermal, for seismic, and we have low efficiency, low carbon, low emission combustion. So we've got combustion engine design. We want to run these engines as lean as we can and reduce the emissions as much as we can. And so there's a lot of fundamental simulation that we think can lead to next generation internal combustion engine design. Carbon capture, trying to better understand how do we compress CO2, get it underground into stable configurations. So there's a lot of simulation that can be done to support that. So so this is an eye chart that you can have later to take a look at. But let me take you through a few more pictorial examples here. Okay. So on the nuclear energy side, one that I'm familiar with, having spent the last 5 years or so thinking about how to simulate and operate a nuclear reactor. Here you have a interesting team that's proposing to put together Monte Carlo neutronics and particle-based fluids. So in a reactor, you have neutronics and fluid flow. You have fuel. And these reactors can be 12 to 15 foot high if they're full-size reactors. If they're smaller, they still may be 6, 8 foot high and 6, 8 foot in diameter. They could have 20, 30,000 fuel rods. So very complicated beasts. As one of my colleagues says, a very complicated way to boil water. But there you see, in this case, we're going to be focused on next generation small modular reactors. And what I have in words underneath there are the national strategies that these applications support. There's the President's Climate Action Plan, there's SMR licensing support, and something called GAIN, which is a innovation initiative in the DOE Office of Nuclear Energy to impart more innovation into the field, especially on the simulation side. Climate is a really big one that I have a few separate slides on that. We have an interesting proposal from the ACME team, which is the project within the DOE for global climate. And I mentioned carbon capture and storage, wind, and I think I've got some separate slides to show there, as well as combustion. So these are 5 examples, and in parentheses are the Department of Energy offices. NE for nuclear energy, BER is biological environmental research, FE is fossil energy, EERE is energy efficiency and renewable energy, and BES is basic energy sciences. So again, as a DOE Exascale project, we have these program offices who have specific missions to conduct fundamental and applied R&D. And what's happening is simulation is becoming much more of a key part of their portfolio and a key crosscut. And so we are specifically targeting applications that target their high priority strategic initiatives. I mentioned nuclear energy. One way to think about it is, why do we need to do it? Why do we need to simulate these reactors at all? And what's Exascale going to buy us? Okay, and we're using the notion of challenge problems. Paul may have alluded to that, but we want to target a specific problem that we want to build the code to simulate that really requires Exascale class capabilities. Okay, and is programmatically impactful. So. Has to make a difference in the strategy for nuclear energy in this country. And we're not going to claim that we're going to solve the problem. We may or we'd like to, but we are going to claim we're going to develop the simulation capability to simulate that problem and then better understand that problem and ultimately be part of the solution. Okay? And so there you see what the teams have put together. And this particular approach is using Monte Carlo, lots of particles, and like I said, fluids and solids in the form of particles that mass very well, we believe, to Exascale, and so it'll require some more or less major sort of rethinking of particular algorithms, in particular for fluids and solids. And my own experience in modeling nuclear reactors is from the Castle Hub, and I'll just say that when we sat down and talked about reactors, most of the fields can take you through what it means to go from terascale to petascale to exascale. And, and I think the last slide of my talk, I'll kind of get to what the 5 or 6 sort of fidelity axes are for applications. But, as you move up in compute capability where you have more memory and more speed, now you can begin to knock down assumptions associated with geometry. You don't need to assume things about geometry. You can be truthful, faithful to the geometry. You can knock away assumptions with your models. You have less and less assumptions in your models. You can solve your problems more accurately, more quickly. And so now you begin to say, okay, my application is more predictive, and one way to measure that is my error bars in my simulation, which is hard to quantify, are now smaller. Okay, and they're smaller where it matters. On the climate side, the ACME team has put together some really interesting proposals that we're considering. And in this case, they want to be able to do many, many 100-year simulations. And right now, they can get about 5 model years per day. Okay, so to do a century simulation, because climate timescales are not weather, again, they're centuries, it takes 20 days. So what they want to do is they want to maintain the 5 simulated years per day, but they want to go down to 1 kilometer instead of their current 35 to 40 kilometers. And within 1 kilometer, okay, you still might have multiple clouds, right? So you're not necessarily cloud resolving. To get down there, you need to be order meters or tens of meters. But with 1 kilometer, they can super parameterize the cloud and basically think of that as they can do DNS or LES, separate simulations of the clouds, and then upscale them into the 1 kilometer global climate. So this one has more than an atmosphere. Obviously, you have an ocean, you have land ice, you have sea ice, and at some point later, you'll also have groundwater, which is subsurface. And so tremendous compute capabilities and compute requirements. And this group has recently moved, well, in the past sort of 3 years or so, moved to pretty much all unstructured meshes. And they used to have, for the atmosphere and the ocean, or at least the ocean, long meshes, latitude-longitude meshes. They moved to cube sphere and dodecahedrons, which I think make much better sense in terms of mapping where the action is, which is often near the coastlines, let's say, for the ocean. So again, you can see some of the perspective outcomes, and you know what their key challenge problem for Exascale is regional assessment of climate change. Okay, we're beginning to see in certain areas of the country, as an example, we have more violent storms and less rainfall or more rainfall, and so need to be able to, they want to do quantitative regional assessments of climate change to inform our policymakers, because we're really in the climate change game. We're really into the adaptation and mitigation scenarios. Okay, and so that's a really important application for us in ECP as well. Carbon capture and storage. This is a very important area for clean coal. And you know, I think in the interest of time, I'll keep moving unless there are specific questions. We have an interesting wind energy application, a National Renewable Energy Lab, and what they've and being more of a CFD person myself, for a single wind turbine scenario, they've been pretty darn good at being able to understand the turbulence associated with a single wind turbine, understanding how to sort of maximize energy return. But not so good or even good at all understanding how 49, in this case, 49 wind turbines interact with one another. And there what they're seeing is, for a wind plant, you're seeing up to 20–30% loss of efficiency, okay, relative to what they think they can get just because of interactions from wake to wake in the turbines. Okay, so they want to do a full wind plant simulation. They want to couple it with a weather code like WRF, okay? And so have faithful representation of the local terrain and the weather. All those things interact. You've also got fluid structure interactions too. So now you ideally like to model the structure of the turbine blade. So really, in my mind, a way cool problem, very compelling, and I think very doable, albeit difficult. But you can see some of the potential returns on even just a 1% wind plant performance improvement could translate into hundreds of millions of dollars in annual savings. So this is one that we're looking at. I mentioned the combustion area. Lots of really good research going on in Argonne here, at Sandia National Lab, at Berkeley. Again, looking at designing engines that burn leaner and have reduced emissions. In this case, doing everything from a DNS of a very small sort of cubic centimeter size flame front to understand the turbulence there, then upscaling that information into a full-blown engine scale code. Some other examples I mentioned. See, magnetic fusion energy. I mentioned advanced manufacturing. Chemical sciences here is actually designing catalysts on the computer that can accelerate or enable certain reactions. In this case, breaking down cellulosic-based chemicals. We do have one NCI NIH application that's just way cool, and I am not a biologist, so I'll do my best to take you through that. But we're likely to see more of these applications come into our portfolio, where DOE lab people are working with the domain scientists to build large-scale simulations. So in this case, well, I should not have a slide on it, so I'll say a little bit more now about it. This is precision medicine and oncology, and there's sort of three areas that are being focused on. One is really the molecular level, sort of understanding the drug treatment issue and how the RAS-based cancers grow. Another one's at the cellular level, so now cells or groups of cells, and then the last one is really what I call population health or above the skin simulations, and that's trying to understand how your environment and how you live influences your ability to get these cancers if exposed. Urban system science. So that's what I want to call a very non-traditional HPC application. Urban system sciences is another non-traditional HPC application, and so we're going to see. We're interested in the ECP in taking a hard look at these non-traditional applications and potentially supporting them. So urban system sciences, the idea is you'd like to be able to inform a city planner if you were to build a new traffic system, say a new bridge or a new set of highways, in 10 years, this is how things might look, okay? So, where to put infrastructure, where to put your where to transmit energy, where to produce energy, issues associated with water, communication, interconnectivity. So basically the idea here is an Exascale application that would essentially inform city planners on what-if scenarios for their city relative to what they're doing today. So way cool problems, that's for sure. So magnetic fusion energy, a little deeper dive here. And in this case, this team out of Princeton is looking definitely at magnetically confined plasmas, in this case the tokamak, the donut shape that's associated with the ITER facility, but also the simulation environment, which is going to be coupling core plasma physics with edge plasma physics, is being designed to be more flexible with other interesting geometries like the stellarator or in Germany, the W7X is looking very promising with regard to confinement times. So I mentioned the additive manufacturing, and so I think we're all seeing just the wonders of 3D printing. We've seen cars printed, we've seen even houses or small homes printed. But where the real issues lie and the challenges lie is with metal alloys. And for many areas, let's just take a nuclear reactor for example. It's full of metal alloys, and right now you can't 3D print a metal alloy with the quality that you need for some of these applications. By quality, I mean there has to be certain strength properties, there has to be certain alloying element properties that you can't control well in a 3D print. So the idea here with this simulation is to be able to actually simulate, whether it's with laser or E-beam, the 3D printing process, the actual melting of the powder layer by layer up into a part, and being able to not only predict, but dynamically control where if I'm zapping the powder with a laser, to be able to say, you better go back and remelt that because the porosity wasn't right, okay, or the interstitial mix wasn't correct. So in this case, it's actually simulating a 3D printing process, really to try to better qualify metal parts. Other application areas, I mentioned materials, just ubiquitous everywhere. So we've got a bunch of material science projects that are going to be focusing on, really in support of the MGI, which is a Materials Genome Initiative. And as I said, this is materials discovery and design. And here you've got everything from quantum Monte Carlo methods to DFT methods on up through molecular dynamics. So you've got this suite of different codes that reflect different assumptions in the physics, all at play here with regard to the materials. Again, there's another combustion project we're looking at, cosmology. Fundamental questions are being answered there. Particular dark matter postulated, I guess, 1922. We're almost approaching a century. I believe that in the high energy physics community, coupled with cosmology to validate, we're going to see dark matter understood and explained in the next 10 or 20 years. And I think that this is Doug's opinion that large-scale computing will play a large role there. Let's see. Again, we've got a number of other applications. I think in the interest of time, I'm gonna just wind down here. But these are essentially 30 of what we believe are some of the most important areas in the DOE where Exascale can make a difference. Let me say something a little bit about co-design and then wrap it up. So I don't know if you've been introduced to the concept of co-design, or you may during these next couple of weeks. But it's very important for applications to be able to perform well relative to where they are now and given the hardware that's coming. So what we've done is we want to support a broad set of applications, and every application will likely need to do some level of co-design, which is intimate, sort of back and forth, push-pull, with not only the software stack, in this case the runtime system, compilers, et cetera, but even the hardware. But in our case, what we've done is we've said, let's look at the motifs at each application. And again, we're calling a motif a sort of common pattern of communication and computation. And this notion isn't new. I think it was first brought out by Phil Colella at Berkeley with his 7 motifs. And then I think about 10 years ago, another 6 were added. So these are examples of 13 motifs, and you can kind of see the words there with regard to what they are and what they mean relative to certain patterns of communication and computation. And in looking at the applications, we see that all these applications typically have 3 or 4 of these motifs. And so if we can co-design these motifs to really rock and roll and scream on the next generation systems, and see the co-design process not just emit best practices and sort of rules of thumb for how to implement the motifs, but even next generation libraries and components that are used by the app. So example, think of particle and cell. Why not have a co-designed activity looking at particles, how best to push particles in a mesh, how best to map particles back and forth. And those are essentially motifs that could essentially form a next generation library that particle codes now are using, rather than they're all rolling their own now and they all have their own different data structures and they're all doing things different ways. So that's an area we think we can leverage better, is going after motifs. And so we've done things like this. We've said, okay, let's look at a particular application, and the green here means that motif is used. So you can see some of the data science motifs, the kind of the other 6, we don't have the coverage yet that we think we need. And here, data science is, machine learning is a classical example, but there's lots of other examples. And as Paul, I think, mentioned yesterday, we're very interested in and will be supporting data science applications. The NIH one is going to do a lot of machine learning at scale in support of the precision medicine for oncology. But we also got these large data centers, whether it's, in this case, LCLS is one we're looking at, going to be producing a lot of data. We want to be able to analyze that data real time and develop it into an Exascale class workflow. So these other motifs are going to be really important to get a handle on. I really like the Sandia model, Sandia National Lab model for predictive maturity. So I'll just end with this. In the end, we really want to be able to, we want to have a bunch of applications that are ready to go when the big systems roll in. They're ready to answer consequential questions for the nation in these areas that we talked about. But probably more importantly, we want to make sure that we have high confidence in the answers. And so with regard to predictive capability maturity, I don't think anybody would argue with the fact that we need to dissect these applications and make sure we understand their sensitivities and their uncertainties. And there's where we're going to need a lot of help from the program offices and from the applied side in terms of validation and verification. But the point of putting this up is that we, in ECP, what we're going to do is work with the applications team to sort of do a self-assessment, predictive maturity assessment as we go as to how well we're doing. And we're also going to bring independent folks to help assess just how well we're doing with regard to knocking down the uncertainties and getting better, more high-confidence answers. So I'll conclude with the application development sort of mission and objective. But basically, this is a really exciting time for application development. And we're gonna see through not just ECP but other funded initiatives, a lot of need for recruitment and retention of skilled folks like yourself to come in and think deep thoughts and help us move forward.